Welcome back to Bias, Accuracy, and the Statistics of AI Testing. So now we're going to dig into inputs, outputs, and parameter spaces. So let's take, for example, the following statement. Our algorithm can detect suspicious activity from CCTV footage with 83% accuracy. So this is the kind of statement that you might see in an advertisement for an AI system. You might see it in an audit report. And the question is, what does this mean, 83% accuracy? So we're going to be digging into metrics of systems, including accuracy, in future modules. But right now, we want to sort of just wrap our mind around what are the kind of complexities involved in trying to ascertain that kind of number. So I had actually made up that statement. Well, I think when I made it up, I said 95% accuracy or something like that. But with a quick Google search, it turns out, of course, that there is a system out there like that, and you can find places or people who have described how they've trained systems like this. So this is taken from a Medium article. The link is right there. And in fact, they build a suspicious human activity recognition algorithm from a couple of different data sets. They describe the training in quite a bit of detail. So I'd recommend actually poking around and taking a look at that after you watch some of these lectures. And they even have plots of accuracy as they train their system. Here we have a difference between the accuracy of the training data and of the validation data, and we'll get into more details about what this means in later modules. So the real question is, what do we need to find out in order to understand what this number might mean? Because it's, at the face of things, it sounds okay. So you would think 83% of the time it's able to detect whether there's suspicious activity. But what more might we need to understand when we're trying to assess the risk of this system? So what I want to push here is this idea of parameter space, or probably a better term would be concept space thinking. So if, what do I mean by parameter space? I'm going to be pretty loose with this. If you just go to Wikipedia or something, the parameter space is a space of possible parameter values that define a particular mathematical model. And in fact, parameters are often used to describe the weights of certain machine learning models, often. But if you replace mathematical model with sort of conceptual model more generally, then this is the way I want you to think about interrogating these systems. So when I say parameter space, what I really mean is the range of possible situations, the range of possible values that inputs could take, the range of possible values that outputs can take, and the range of contextual situations that this model could be used in. So if there's only one thing to take away from this course, it would be the habit of thinking in this way. So let me take a look at sort of the standard way of thinking about parameter spaces in terms of functions. So a function is, you can think about a function as an algorithm, as the way we've been using algorithm in this course. It's just something that will take a bunch of inputs and map them to outputs. So the parameter space is really the space, in the way I'm using it, is the space of possible values that x could take. So there could be different values of x. They could range very wildly. And the parameter space is the space of all values that these inputs can take. It's also the space of possible outputs that could come from this model. And the classic way of thinking about parameter spaces is the actual variables that define how this mapping happens, which is the actual function itself. So there's a real technical kind of mathematical way of thinking about parameter space. There are various inputs, there are various outputs, and you want to know the full range of that, and you also want to know the full range of parameters in this function. But probably beyond that, or more importantly, there's also the contextual understanding of parameter space. So the classic, and you'll recognize this graph or this illustration from some of our other courses. The basic idea is that we have an algorithm, which is like this function that's going to take inputs, map them to outputs, right? This is the technical portion, but that's embedded in the real world. And so the real world is full of things, objects, people, different situations. And we are going to take measurements of this real world, and there's going to be filtering. We have some sort of conceptual model or measurement model, and we're going to capture the real world in the form of some sort of data. And that data will have a distribution. Those different variables that we're measuring will have a distribution. And the parameter space is really that distribution of all of these different inputs. But also, it's the fact that the world itself has this huge distribution of possible situations. People are different. Not everybody is the same. Not every situation is going to be the same. And so this is the broadest sense of parameter space thinking that I want you to sort of embrace. What are all the possible permutations of these variables, and how much did the testing actually cover? So another way of looking at this is the sort of socio-technical parameter space. So if we look at our CETA narrative, there are a range of possible contexts, and I'll give you an example in a second. There are a range of possible contexts that an algorithm could be used in. There are a range of inputs and values that those inputs could have. There's a range of inferences that could be made, and a range of human judgment in this socio-technical context. There could be different people using the outputs of this decision to take actions. Of course, there are model parameters. There's a parameter space of models. There are different types of models, and even the same type of model can have different weights or parameters. And then there are a range of actions that can be taken and a range of consequences. So the testing, you should think about the testing that happens that gets you an 83% accuracy is going to be over some subset of this entire parameter space, the socio-technical parameter space. So let's go back to the example that we had, the suspicious human activity detector. So context, under what conditions is it actually used? So where is it used? Is it something that's used in a subway? Is it in a shopping mall? Is it used in underground garages? There are different people. So when I say people, this could be different groups of people. It might be demographic groups. It could be different locations. So the place could determine the people. So it might be used in different countries. There might be different lighting situations. It could be used in different times of day. So that's just the context, and there's a wide range of that. So you have to think about where was the testing, what's the context under which this testing was done, and how does that compare with the context in which the algorithm is actually going to be used. There are inputs, of course, so how is it measured? So that could be camera quality. Not every CCTV camera is going to be the same. There are different resolutions. There might be different frame rates. How is it processed? So maybe it's processed only a certain number of frames. Maybe there's some pre-processing like smoothing or lightening of the images or video. Is sound used? Typically not, but potentially could be used. What about the decision procedure? So what kind of model? Is it a CNN, which is a convolutional neural network? Is it an LSTM, a long short-term memory network? More likely nowadays, it would be some sort of transformer model. What are the number of parameters? How about temporal variations? Is the model consistent the entire way through, or does it change? Is it being trained at a particular cadence? When was the testing done relative to the parameter space of those changes? Is it probabilistic, or is it a static model where you're going to get the same result for the same input? Or is there some sort of probabilistic element to it? And what are the possible output values that you could get? Is it just a binary 0 to 1? Typically, if it's some binary classifier, there has to be some threshold value that is chosen, because most of the time these systems will not output a 0 or 1. It will be something between 0 and 1, and you have to pick a threshold, like above 0.6 is suspicious activity, or above 0.8 or something like that. So those thresholds matter, and how is the testing done relative to those thresholds? And then of course there's the action taken. So who decides what happens when a suspicious activity is detected? What are the range of actions that could take place? Is it just some sort of warning? Are they just logging it? Is it going directly to the police? Is there police interventions? This could affect how we might test the system. So the real question when we're faced with a number like 83% accurate is, over what range of this entire parameter space was the system tested to get that accuracy metric? Because that's really what it's telling you. You look at that parameter space under certain conditions, you narrow it down, and the testing data is going to exist in a small portion of that parameter space. And so that number is really only relevant for that piece of this really broad parameter space. And when you're thinking about risk, you have to think about, does the risk, is there good coverage of that parameter space in the areas where risk could occur? Let's say low lighting. If it's operating in an underground garage where lighting is low, it could be very risky. There may be less or some degradation of the accuracy under low lighting conditions. Has that been tested in those situations? And so that's a relevant thing to ask. So what we now have to do is we have to start quantifying this parameter space. And so we're going to start delving into a little bit of statistics, probability, and sampling theory.